Digital multimeter is a good example for round robin architecture, where in a digital multimeter, when the switch position is in ohms resistance, then the switch position is being checked in this while loop. Whenever it is in ohms, it will read the hardware to measure the ohms, and then it format the results. And then if it is ohms tens position, it will read the hardware to measure ohms, and then it will format the results, and then it will break and it will read the hardware to measure volts if it is in the volts case, etc. So resistance, volts, currents, etc. like that. All the switch positions are checked in round robin fashion, and based on the switch position, the corresponding case will get executed, and then the corresponding reading will get displayed in the multimeter output, which is round robin architecture, as we know very well. Okay. So in this round robin architecture, here if we see, okay, this round robin architecture, first it will serve the IO device. First it will serve the IO device A. So for example, if IO device A needs the service, take care of IO device A and handle the data to or from the IO device A. If the IO device B needs service, it will take care of the IO device B and handle the data from IO device B. Similarly, etc. up to IO device Z. Okay. So this is the round robin. So A to Z, all the tasks are executed in sequence, and if the corresponding device needs a service, and then based on the requirement, it can read or write the data into the corresponding IO devices, device A, device B up to device Z. Okay. But the one important thing which we have to notice here is, if you look at this, if any one device needs response in less time than it takes the microprocessor to get around the main loop, in the worst case scenario, then the system won't work. Okay. So the timing, if we consider the timing, if the timing is very important, means then round robin architecture will not work fine. So let us take one example here. So in this figure 5.1, in this example, the device Z can't wait for more than 7 milliseconds. Let us say, for example, the device Z need to be serviced once in 7 milliseconds. So for example, the device Z need to be serviced once in 7 milliseconds means, and device A and device B takes 5 milliseconds to execute. Let us say, for example, device A takes 5 milliseconds to execute, and device B needs 5 milliseconds to execute, and device Z within 7 milliseconds it has to execute. Means after executing the device A and device B, if it come and executes the device Z, means device Z will miss the deadline. So what we are supposed to do, we can make device Z to execute after device A. So IO device A needs service, then you can write this function if statement here next to IO device A needs service. We can write if IO device Z needs service, then after 5 milliseconds A task will be over, then it will execute the Z task, then B task will be over, then we have to write the same function Z task, then C task, then Z task. Like this, if you write the functions, means it can serve the purpose, but it is very difficult, right? Let's hope you understand the concepts here. Okay, so that is what being mentioned here. If the device Z can wait no longer than 7 milliseconds for service, means if the piece of code that service device A and B takes 5 milliseconds each, means the processor won't always get the device Z quick enough. Now we can squeeze this like a little more out of the round robin architecture by testing device A, then Z, then B, then Z, and so on. But there is a limit to how much of this we can do. So the world is full of IO devices that need fairly rapid services, like serial ports, network ports, push buttons, etc. Hence round robin may not meet the purpose of timing requirements. If there is no timing requirements for the application, then we can go for round robin architecture. If there is a timing requirement, round robin architecture may fail any time to meet the timing requirements. Say for example, that's why this architecture is fragile. Even if you manage to tune it up so that the microprocessor gets around the loop quickly enough to satisfy all the requirements, single additional device or requirement may break everything. Because of this shortcomings, the round robin architecture is probably suitable only for very simple devices such as digital watches and micro ovens, as possibly not even for those. That is very important. So then we go for the round robin with interrupt architecture. So in this David E. Simon book, the chapter 5.2 talks about round robin with interrupts. Round robin with interrupts means as like how we execute the code with interrupts. Okay. So round robin with interrupt code means here there is interrupt handle device A, interrupt handle device B. All the interrupt service routines are executed, and the main routine will have the device A and then device B and then device C, etc. So main routine will have the task codes with equal priority, and the interrupt service routine will have the highest priority. So now the interrupt service routines are having highest priorities and main routines are having the equal priorities, which is round robin with interrupt architecture, as like how we write a simple C program in our 8051. Here we used some code to experiment the shared data problem. The same code is being shared here, right? So here we can see the main routine is comparing the temperature, and the interrupt service routine is updating the temperatures. So interrupt service routine is having highest priority and the main routine is having the lowest priority, but both the interrupt service routine and main routine are sharing the common variable, which is temperature 1 and temperature 2. And this is the good example for round robin with interrupt architecture. So when we look at this architecture, the interrupt routines deal with very urgent need of the hardware. The main loop executes the tasks in sequence with all the tasks having the equal priority. The priority levels of round robin architecture are shown in the figure here. Okay, so the highest priority is in the top and the lowest priority processing is in the bottom. With respect to round robin architecture, all the tasks are having the equal priority, but with round robin with interrupts, you can see device A interrupt service routine is having highest priority, then B interrupt service routine is having highest priority. Like this, all the interrupt service routines are having the corresponding priorities, and all the task codes are running with equal priority. If there is no interrupt service routine, task code will run. If there is an interrupt service routine, because interrupt service routines are having highest priority than the task code, program execution jumps to interrupt service routine, as we know very well. Okay, so this is round robin with interrupt architecture, and the third architecture talks about function queue scheduling architecture. Okay, so which is with respect to this author, function queue scheduling architecture. The good example for round robin with interrupt is a simple bridge. So network bridge. Okay, here the communication link A and the communication link B. Here the data forwarded from B to A, and here the data forwarded from A to B. So this communication bridge is a good example for round robin with interrupts, where normally the audio packets will be given highest priority when compared to the video packets. So whenever there is an audio packet, that will run an interrupt service routine. Whenever there is a video packet, that will run in a main routine. Something like that you can understand. So good example for round robin with interrupts is a communication bridge. Is a good example with respect to David E. Simon. And when we look at round robin with interrupt, according to author, the cordless barcode scanner is also a good example for a round robin with interrupts, and laser printer and underground tank monitoring system are other examples for the round robin with interrupt architecture. When we come to the function queue scheduling architecture, this is function queue scheduling architecture, where yet more sophisticated architecture, what we will call a function queue scheduling architecture. In this architecture, the interrupt routines and add function pointers to the queue of function pointers for the main function to call. So main routine just reads the pointers from the queues and calls the functions. Here you can see. So if the device A needs the service, so it go to the interrupt service routine and then put A function on the queue. The interrupt service routine need functions, put B function on the queue. In the main routine, it executes all the queue functions, right? So QA function means QA function handling will happen separately, QB function handling will separately. So adding to the queue will happen in the main routine. So it executes in the interrupt service routine. This is function queue scheduling architecture. with respect to David E. Simon. Then the real-time operating system architecture. When we come about the real-time operating system architecture, the only difference is the interproteins are having priority and the tasks are also having priority. You see, task 1 is having its own priority, task 2 are having its own priority, it goes on. Okay. So when we compare the priority levels of real-time operating system means, if you compare with round robin with interrupts architecture, in the round robin with interrupt architecture, device A to Z are having the priorities, then all task codes are having equal priority. But in the real-time operating system, the task codes are also running with the priority. So that is the only difference that we have to focus. Real-time operating system, interrupt service routines are also having the priorities, and main routine task codes are also having its own priorities. So every function which is called as task in real-time operating system needs some priority, and based on the priority it executes. That is the only thing we have to concentrate with respect to real-time operating system. So when we talk about the characteristics of real-time operating system, characteristics of various software architecture with respect to this Simon Mather book, here the survey of software architecture is very clearly given. The same function queue scheduling architecture is being discussed, and the real-time operating system task is also being discussed. And when we look at the characteristics of the various software architecture, here if we see the priorities, with respect to round robin there is no priority. With respect to round robin there is no priority for any tasks, it runs in the sequence. But when we compare with round robin with interrupt architecture, the interrupt routines runs in the priority order, then all other task codes at the same priority. With respect to the priority in round robin with interrupts, and in the function queue scheduling architecture, interrupt routines runs in the priority order, then the task codes would also runs in the priority order. Similarly, in the real-time operating system, the interrupt routines runs in the priority order, then the task code runs in the priority order. Okay. With respect to the priority, real-time operating systems, interrupt service routines are also having the priorities, main routines are also having the priority, that we need to understand. When compared to the worst case response for a task code, so task code which runs in the main routine, what is the worst case response? Sum of all task codes with respect to round robin, because it is round robin, all the tasks need to be executed in sequence, and whenever the turn comes, this particular task code will run. That is why sum of all task code time is the worst case response time for the task code in the round robin architecture. Worst case response time for a task code in the round robin with interrupt architecture is total of execution time of all task codes. As usual, total of execution of all task codes, but in between if the interrupt comes, interrupts are having highest priority, so the time required for interrupt service routine need also to be considered. So plus the execution time for the interrupt routines. Okay. So the worst case response time of task code in round robin with interrupt architecture is total of execution time for all task codes plus the execution time for interrupt service routines, as we know already. Similarly, the worst case response time for a function queue scheduling architecture is execution time for the longest function plus execution time for interrupt service routine. And with respect to real-time operating system, the worst case response time for a task code is 0 plus execution time for interrupt service routine, because task codes are also given highest priorities. When the highest priority task is in need of the processor in the real-time operating system, immediately the task will go to the running state. But if there is an interrupt service routine, that interrupt service routine time need to be considered. That is the only thing. So initially the worst case response time for a task code is 0 in real-time operating system, which need to be focused much with respect to this characteristics. When we compare the stability of the response when the code changes, just now we have seen, right, the task is when it has to run on before 7 milliseconds means we have to reschedule all the task codes. It is very difficult in round robin. That is why the stability of the response when the code changes in the round robin means it is very poor stability with respect to round robin architecture. The stability is good for interrupt routines and the poor for task codes in round robin with interrupt architecture, and the stability of the response is relatively good in function queue scheduling architecture, and the stability of the response when the code changes is very good with compared to the real-time operating systems, as we see here. And when we look at the simplicity feature, the round robin architecture is very simple. As we know very well, round robin architecture is very simple as we write our conventional 8051 coding C programming, and when compared to the round robin with interrupts, which should deal with data shared between interrupt routines and task codes. So there may be a possibility of shared data problem. That is the only thing that we have to concentrate. Otherwise, round robin with interrupts are also more simple, as we like how do we write timer 0 interrupt service routine, extra interrupt 0 interrupt service routine, etc. in our conventional 8051. And here with respect to function queue scheduling architecture, it is also the simplicity, must deal with shared data and must write function queue code. The function queue code we have to write. But with respect to the real-time operating system, when we talk about the simplicity, which is very complex, much of the complexity is inside the operating system itself. So when you work with real-time operating system, the complexity is more. That is what we need to concentrate. So these are all the 4 characteristics of the 4 different architecture which is tabulated, and we need to focus much on this with respect to the software architectures. Thank you.